Imagine waking up on Mars, breathing the air, walking on green plains. Sounds like science fiction, right? But what if we told you, with radical breakthroughs, we could make Mars habitable in just 100 years? The challenges are monumental, but the solutions might shock you. Stick with us as we explore the audacious plan to transform the red planet. First things first, Mars is cold, really cold. The average temperature is a bone-chilling -80 degrees Fahrenheit or -62.2 degrees Celsius. It also has a whisper-thin atmosphere, about 100 times less dense than Earth's, and it's mostly carbon dioxide. This means no breathable air and no protection from harmful solar radiation. So, how do we fix this? The first step is to warm the planet up and thicken its atmosphere. The key ingredient is already there, frozen carbon dioxide locked away in the polar ice caps. The big idea: we need to release that CO2. A popular concept involves building giant orbital mirrors. These massive mirrors, miles across, would focus sunlight onto the Martian poles. Think of it like a cosmic magnifying glass. This intense heat would sublimate the dry ice, turning it directly into gas and pumping trillions of tons of CO2 into the atmosphere. This kicks off a runaway greenhouse effect. As the atmosphere thickens and the planet warms, more CO2 and water vapor trapped in the soil would be released, accelerating the process. Within a few decades, we could potentially raise the temperature above freezing. But a thick CO2 atmosphere isn't breathable. We need oxygen. This is where biology comes into play. We'd start by introducing extremophiles, hardy microorganisms from Earth that can survive in extreme conditions. Think algae and lichens that thrive in Antarctica or deep-sea hydrothermal vents. These tiny pioneers would be seeded across the Martian surface. Through photosynthesis, they'd begin the slow but steady process of converting carbon dioxide into oxygen. We're not talking about lush forests just yet, but the first green blush on the red planet. Simultaneously, we'd need to create a magnetic shield. Mars lost its global magnetic field billions of years ago, which is why its atmosphere was stripped away by the solar wind. Without protection, any new atmosphere we build would suffer the same fate. One ambitious proposal is to place a giant magnetic dipole shield at a stable Lagrange point between Mars and the Sun. This would act like an artificial magnetosphere, deflecting the charged particles of the solar wind and shielding the planet. It's a colossal engineering challenge, but theoretically possible. With a warmer planet, a thickening atmosphere, and a protective shield, the next step is water. Mars has vast quantities of water ice at its poles and buried underground. As the planet heats up, this ice will melt. We'd see the return of rivers, lakes, and perhaps even small oceans in the northern lowlands. This liquid water is the lifeblood of our terraforming project. It would stabilize the climate, support more complex life, and be essential for future human settlements. We could even accelerate this process by using targeted impacts from comets, which are essentially giant, dirty snowballs from space, to deliver more water and other vital volatile compounds. Now, let's talk about the 100-year timeline. It's incredibly aggressive. The initial warming phase with orbital mirrors could take 20 to 50 years. Introducing primitive life and waiting for it to produce a significant amount of oxygen would take much longer, potentially centuries. So, how do we speed it up? This is where radical breakthroughs come in. Imagine fleets of self-replicating robotic factories blanketing the planet, processing the Martian regolith to release trapped oxygen and building infrastructure. Or perhaps, advanced genetic engineering could create super photosynthetic organisms that produce oxygen at a rate hundreds of times faster than anything on Earth. These oxygen factories would be our workhorses. We could deploy them across the planet, creating oxygen-rich pockets around early human habitats. Initially, settlers would still need to live in pressurized domes and wear breathing apparatus when outside. But as the atmospheric oxygen level rises, first to a few percent, then to 10, then eventually to a breathable 21%, the need for life support would diminish. The first time a human could take a deep breath of Martian air without a helmet would be a milestone for all humanity. Creating fertile soil would be another major task. Martian soil or regolith lacks the organic matter necessary for most Earth plants to grow. Our pioneer lichens and microbes would begin this process, breaking down rock and fixing nitrogen. But to speed it up, we'd import earth, soil, and compost, and use advanced hydroponic and aeroponic farms within our biome. These farms would not only feed the colonists but also produce organic waste that could be used to enrich the Martian land. Over decades, patches of barren red dust would slowly transform into dark, rich soil, ready for earthly grasses, shrubs, and eventually, trees. Imagine the first forest on Mars. Genetically engineered trees designed to withstand lower gravity and higher radiation levels. Their leaves soaking up the faint Martian sunlight. The sight of green under a pinkish-tan sky would be a testament to our perseverance. The ecosystem would be carefully managed, introducing insects for pollination, worms to aerate the soil, and eventually, small animals. We wouldn't just be building a new world, we'd be curating a new biosphere. Of course, the ethical questions are as massive as the engineering challenges. Do we have the right to fundamentally change another planet? What if there's microbial life on Mars we haven't discovered yet? Transforming the planet would surely destroy its native environment. This is a debate that will and should continue. Any plan to terraform Mars must proceed with extreme caution, prioritizing scientific discovery and planetary protection. Perhaps the initial stages would focus on creating isolated para-terraform zones under massive domes, preserving the rest of the planet until we are certain it is lifeless. So, could we terraform Mars in 100 years with our current technology? Absolutely not. It would take centuries, if not millennia. But the question assumes radical breakthroughs. If we develop fusion energy, advanced AI and robotics, and master genetic engineering, the timeline shrinks dramatically. 100 years is not about a specific guaranteed date. It's a vision, a goal that pushes the boundaries of what's possible. It's a challenge to our scientists, engineers, and dreamers. The journey to a green Mars is a marathon, not a sprint. It would be the most ambitious project ever undertaken by humanity, requiring a level of global cooperation we have never seen before. But imagine the result: a second home for humanity, a backup for life on Earth, and a symbol of what we can achieve when we reach for the stars. The dream of walking on a green Mars is powerful, and sometimes, a powerful dream is all you need to start making the impossible possible. What do you think? Is terraforming Mars an inspiring destiny or a foolish dream? Let us know your thoughts in the comments below. And if you enjoyed this journey to a future Mars, don't forget to like this video and subscribe for more explorations into the future of science and space. Thanks for watching.